Okay, so we are halfway through learning our 10 tests for convergence slash divergence. As a quick recap, test one is telescoping series. See if you can name them before I get to them. Test two is geometric series test. Third is the nth term test for divergence only. Fourth is the integral test. Positive, continuous, and decreasing. And fifth is the p-series, whether p is greater than 1 or less than or equal to 1. All right, those are all great, but they all the ones that converge specifically, like the nth term test doesn't have to be anything in particular, but the 1, 2, 4, and 5, those are very particular sorts of series. These are series that are either fitting in this category of telescoping or geometric, or we can integrate them, or they're exactly a p-series. Now, what happens when we look at a series that looks kind of like one of those, but is not quite that? For example, 1 over 2 to the n is geometric, but n over 2 to the n is not. It seems like it's geometric. It seems like it might be related to geometric. It is, in fact, but related. It is related, but it's not exactly the same thing. So we can't use the geometric series test for that. P-series of n cubed in the denominator? Yeah, perfect. But n cubed plus 1, that tiny little change, means that it's not technically a p-series, and we can't use p-series alone to deal with that. Here's a positive, continuous, and decreasing function that we can easily integrate using u substitution. U equals x squared plus 3. But now that we changed this to an n squared on the top, we can't integrate that easily. But they sure do look very similar. So if only we could have some way of comparing, oh, wait a second. Comparing the comparison tests. We're going to compare these series that look like familiar ones but are a little different. We're going to compare these similar ones to the ones that we know how to deal with. So we've got the direct comparison test, which is the 6th test, and the limit comparison test, which is the 7th test. And these two tests are going to open up the door to even more series that we can deal with. Now here's the trick, guys. If we're going to use a comparison test, we can't use it without using some other test. So we can say that this thing does something if we compare it to this one, but we have to say what this one does based on one of these older tests. So the comparison tests always require the use of one other test as well. So that they get a little bit longer in use because you've got to prove a different series before you deal with the series in question. All right. So let's start with the direct comparison test. That one's the easier one conceptually, I think, because all it says is we're comparing two different series, and the terms and the sequences of those series, one term is always less than or equal to the other. Without loss of generality, we'll call A sub n the smaller one and B sub n the larger one. So we've got this one is the smaller one, and this one is the bigger one. Okay? So basically what this is saying is if the bigger one converges, then the smaller one has to converge as well. Of course it does, because it's going to converge to something smaller than the bigger one. Conversely, if the smaller one diverges, then the bigger one diverges. Think about that. If the smaller one is infinite, if the smaller one goes off to infinity, then the bigger one's just going to go off to infinity, right? It's going to go off faster. So this is kind of a conceptually obvious one once you think about it. The only trick is determining what your two series are. One of your series is going to be the given series. So either this is going to be A sub n or is going to be B sub n. We don't know which until we decide what we're comparing, right? All right, so we take a look at, well, actually, this one's kind of a trick, isn't it? We don't want to compare this to anything. What's the better test to use? Think about that. Look at these. You'll notice that the degree on the top is the same as the degree on the bottom. So what is the limit as n approaches infinity of this? Of course it's 1, right? And the important thing about that limit is that it's not equal to, 0. If it's not equal to 0, then we can say the series diverges by what? Yeah, the nth term tests. Yes. So what's that one doing there? Maybe it's just a little bit of spiral review. Thanks, Mr. Corpy. All right, so let's take a look at this one. This is one of the ones in the example earlier. It looks an awful lot like a p-series, right? If it weren't for that pesky +1, that makes me angry. So I'm going to compare the terms in the given series to the terms in the one that I know how to deal with. Now, I want you to think about this. This has a bigger denominator than this, right? We're adding 1 to our denominator. It's a positive denominator. We're adding 1 to our positive denominator. That makes the denominator farther from 0, which means that the fraction is closer to 0. So that means that this original one is less than the one that we know how to deal with. So think about this. We know the one we know how to deal with converges by p-series, right? Because p is equal to 3, which is greater than 1, okay? So we've proven now that this thing converges, but this one is the bigger one. And if the bigger one converges, then the smaller one has to converge to something smaller. Therefore, the given series also converges by, well, we just directly compared this to this one. This is by the direct comparison test. This is an acceptable abbreviation. Anybody grading a calculus exam will know what DCT stands for, so don't worry about writing out the whole thing, just write DCT. And we're done. That's the first example of direct comparison test. Remember that even though we're using the direct comparison test for the given series, we still had to prove the other one using some other strategy. All right, good. So that's always going to be the case with every comparison test, whether it's the direct comparison or the limit comparison, which we haven't gotten to yet. Okay, so again, this one looks very similar to a geometric in this case. Compare the given sequence of values of 1 over 3 to the n plus 2 to, again, that plus 2. This is that extra piece that we don't like. We're just going to take that out. We're going to compare these. Once again, we see that that plus 2 makes this fraction smaller than the easier one. All right, so let's consider the easier one. This is 1 over 3 to the n converges by, well, we're multiplying by 1/3 each time, right? So that's a geometric series test. So it converges by geometric series test because the absolute value of r, which is equal to 1/3, is less than 1. Yay. All right, so because this converges, then we know that the bigger one converges, which means that the smaller one, of course, has to converge. So we can now say that the given series converges by the direct comparison tests, right? We like direct comparison tests because it's so simple, but we need to make sure we state that inequality at the beginning, and we need to make sure that we prove the related series first before we go on to the next one. All right, and so those are some nice examples.